Good afternoon, everyone. Thank you for joining me today at the IIPC Web Archiving Conference. My name is Alexis, and I am excited to present our work on the screen recording-based web archiving of SVOD platforms. This presentation will cover our experiments in preserving DRM-protected content using screen recording techniques. Okay. So today we will cover the following topics. DRM overview. First, we will delve into the basics of DRM, digital rights management, commonly known as DRM. Next, we will discuss the method we have explored to challenge this restriction. Following that, we will discuss on building the toolchain to record the content. And finally, we will look ahead of future direction. Okay, let's dive right in. So our project focuses on addressing the challenge posed by DRM. DRM is technology used to protect digital content from unauthorized access and copying. While it serves an important purpose, it also creates significant hurdles for archivists who aim to preserve digital content for future generation. Before we get into the details, I would like to say a few words about INA, which is the French National Audiovisual Institute. Since 1992, INA has been entrusted with the legal deposit of audiovisual content, which include television and radio broadcast. This mandate was expanded in 2006 to include a portion of web content. While we focus only on French audiovisual content, our colleague at the BNF, French National Library, handles the other part of the web legal deposit. So in this context, we have been asked to experiment with saving protected content, while our direction is working to secure agreements with SVOD platform and the government. So all the following work is conducted under the legal deposit law as part of every experimental project only. And we do not encourage bypassing by any kind of protection. Our primary goal is to preserve both live and stock DRM protected content. By live content, we mean content that is streamed in real time, such as live sports or new broadcasts. And stock content refers to pre-record material available on demand. Also, we want to build a flexible fallback method where direct downloading is not possible due to DRM restriction. So, how it works? To understand our approach, it's essential to grasp how DRM works. DRM involves several key components. Video encryption, which makes the content unreadable without a decryption key. License acquisition, where user must obtain a license to access the decryption key. Decryption and playback, which involve validating the user, enforcing usage rule, and finally playing the video. When it comes to preserving DRM-protected content, we have two main options, downloading and capturing. Downloading preserves the original content quality, but comes with legal and technical challenges due to encryption. On the other hand, capturing records exactly what is visible on the screen, bypassing encryption but potentially compromising quality. Our first attempt at capturing DRM-protected content involves using built-in capture tool in Windows 11. We test this approach with a browser like Chrome, Edge, or Firefox. And we encounter significant challenge due to DRM restriction, which led us to explore alternative method. As a result, this beautiful pitch black screen, it was like watching a movie in the dark, literally. While it might seem like an unexpected outcome, it was exactly what we anticipated. After all, DRM is designed to keep content secure, and it certainly did its job well. So we had to get creative and find a new way to capture the content, without ending with collection of black screen. So, DRM protection varied by level. Level 1, L1, represents hardware DRM, with maximum security supporting up to 4K resolution. Level 3, L3, represents software DRM with a minimum security supporting up to Full HD resolution. Understanding this level is crucial for developing effective capture strategies. This led us to the question how we can effectively handle the different level of DRM restriction to ensure successful capture and preservation. Our second attempt focused on L3, protecting video on Windows 11, also with hardware acceleration disabled. Again, same browser, Chrome, Edge, Firefox, on Netflix. This approach showed promise, but still faced limitation. The main one is that because we disable hardware acceleration, we cannot acquire high-definition hardware-protected content, only software-protected. In the image, you can see two red circles, one indicated that we are actually in standard definition, and the other showing that we are effectively at some software security level. However, let's be honest, who wants to watch their favorite show in such low quality? Ready? 950 by 140 resolution, ready? It's like stuck in the late 90s. While the success was great, we knew we had to aim higher. So now we are setting our sight on capturing level 1 protected video. This means tackling our best DRM and finding new way to bypass this security measure. Okay, for L1 protected video, we turn into remote desktop protocol. So the thing is to okay, how it works. RGP client software is used on the user device to connect to the RGP server software running on the remote computer. So you can interact with your distant computer as if you were in front of it. In our case, we use RGP to display and capture level 1 protected video. By running the RGP client on one machine and the interface server on other, we could bypass some protection because only the client will display and record. The generated content is on the server. So now let's see how we approach this next hurdle and whether we manage to capture high definition hardware-protected content. As I said, both the client and the server run in Windows 11. The server played the video while using the same browser, Chrome, Edge, and Firefox on Netflix, and only the client record. So with this technique, we have managed to capture as a good quality content. So the job is done, but of course no. There is some new step, some emerging challenges from our experiments, and we have to tackle this challenge also. So what are the next steps? One of the key challenges we face is to automate the collection process, because actually it was manual step. Developing systems that can efficiently gather data without manual intervention, which is crucial. Equally important is the need to evaluate the source content quality by comparing the resolution, frame rate, and other parameters of the capture content against the original stream. We can identify some disparity. Also need to assess the capture content quality, considering that the player may adjust resolution, bitrate, and other settings based on the network condition. We have to take this adjustment in account to ensure that we remain true to the original content. Another critical challenge is to balance between quality and disk usage, testing various settings and compression algorithms to find the best balance between maintaining high quality and optimizing disk space to store more content. So now let's automate the process and building a screen recording-based toolchain for server environment without a physical screen. So to address this challenge, we deliberately choose Linux, GNU Linux, because building a virtual display on Windows would require more expertise. So additionally, all of our servers already run in Linux. So let's go. Specifically, the toolchain will use FFmpeg to capture the content and playing the content with Firefox. And also, we used some tool to virtualize display and audio. like XVFB or ALSA. Together, these elements provide a flexible and robust solution for recording. So we test our toolchain during the Paris 2024 Olympic Games, capturing over 100 hours of competition footage. Our setups, as I said, include Linux with Ubuntu, XVFB for display, ALSA for sound, and FFmpeg for recording. This real-world test allows us to evaluate the effectiveness of our approach. After capturing the footage, we need to address several key questions to refine our toolchain and ensure high-quality archival content. First, does the recorded content match the original quality? This involves comparing the resolution, frame rate, and other parameters to ensure fidelity. At the time of the capture, only SD content was available. This means we have over 100 hours of competition footage recorded in SD quality with oversized FFmpeg parameters and no compression to work with. Second, how does the compression affect the quality? We need to understand the impact of various compression settings on the recorded content to find the optimal balance. Third, what is the best balance between quality and disk usage? Testing different settings and compression algorithms will help us to achieve this balance. So now we have identified the next step. This section will focus on reflecting on strategies and solutions we can implement to effectively address this key question. Okay. One approach to validate the quality of the capture is to identify a K-matrix for comparing a reference video to the recorded one. To extract meaningful insight from that comparison, we need to recognize and account for external factors that can influence the quality of the capture content, like network, display, or compression. Additionally, we need to control the playback to ensure consistent experience for each piece of content we capture. Each platform can introduce its own set of challenges, as seen in the top picture. One way to address this is by using a tool like picture-in-picture mode of the browser to keep the video player always on top, or utilizing Playwright or Puppeteer to manage control programmatically. I will conclude by discussing the scalability of the toolchain. We have considered using Docker to containerize the toolchain, but we are limited by the number of concurrent streams allowed by platform. For example, Netflix only allows 2 streams at the same time. Additionally, this approach might not be highly relevant for our use case, as the number of French content we are focusing on is not very large and is growing slowly. Furthermore, screen recording is inherently time-consuming and demands significant GPU-CPU resources, which can lead to a drop in quality. Tackling all this challenge is a lengthy process, and we are only at the beginning of our experiments. So I hope this presentation has provided you valuable insight to the challenge and potential solution for handling video protected content. Thank you.